Okay, so we're gonna start by something not too complicated for after lunch. So what we're gonna start to do, like we're gonna have two patches which are quite useful for many things. So the first one is we need, one thing which is really useful when we do rendering is we need to have bounding volumes. So we need to have like either a sphere, generally either a sphere, either a box that encloses geometry.
I'm sorry, can you just start?
Yeah, of course. So one thing we need a lot for rendering, most often we need bounding volumes. So bounding volumes is like generally either a box or a sphere, like a simple primitive, that enclose our scene geometry. So for example, I have a scene here, and it's quite sometimes really useful to know, for example, the bounding box for the whole scene. Because then I can say, if this part is not inside my camera, I can also easily discard things. So now, like, we have two ways to do this. We can do it in compute shader, but that implies a bit of extra things, because here we just have a bunch of sphere, bunch of boxes, few random transformation. And so if we want to do it in compute, we need to add a bit of boilerplate code. So it's also quite really simple to do it in just using the simple pipeline. So here you have this, which will be rendering our bounds. And here, that's like we're just gonna draw a box to show that our bounds are correct. So normally our box should enclose our geometry. So to do this, what we have first, we need what we're gonna say, we're gonna have one texture which contains the minimum of the box and one texture which contains the maximum of the box. So the first thing is we need to do, but we need two textures. So what we need to do is we need to do a renderer, and we're gonna need to use the MRT version, which means we're gonna use multiple render target. So, well, you can change texture size to something a little bit more relevant. So let's say just this. Actually no, we need to change the texture size to something completely different this time. So we need to have our texture size of 1. So now we need the target format. And we said we want 1 for the minimum and 1 for the maximum also. So you have the target count pin here. And we need two targets. We need 1 for the minimum and 1 for the maximum. So now our renderer outputs 2 texture. So the get slice 0 here is our minimum texture, so we need to connect this here and this one here. So the second one gets the max. Like we can see, like we're getting 1 texture for the minimum and 1 for the maximum. So now the format needs to stay like this, RGB float. Like we store a 3D position, so we store 3 points, but we should not use, we should never use 3-channel format texture because they don't work anyway. And 3-channel format texture is a quite bad thing to use in general because you can't sample it. So generally it's like, well, if you try to sample it on ATI or Intel, it's guaranteed driver crash. And actually internally, like 3-channel textures, it's like 3 1-channel textures. That's why they're very hard to sample. So NVIDIA fixed it for you, ATI crash. So when you use texture, you always use 1, 2, or 4 channels. So next, we need to render our bounds. So we have our sphere, we have our box. So like we don't care really about the triangle. We need to get the minimum of each point and the maximum of each point. So that's why we use per vertex drawer. because we just ignore index buffer. Index buffer is not useful by any means because we don't care about the triangle. We just need the bounds of the points, not the bound. So since I mentioned we need the bounds of the points, we also need to change how we draw our geometry. So we need the topology here. And we need to say I'm rendering my geometry as point list instead. And now we can connect it to our bounds renderer that we can in turn connect to our renderer. So now what we need to do is we need to find a way to keep, in this we need to keep the minimum in one texture and the maximum in one texture. So the first thing we need to do is we need to output the position data. So we're gonna consider we want the bounding box in world space, which is the one that makes the most sense. So we can see, like, so for each vertex we have the input position, but like we're gonna do a little twist. We're gonna output every vertex will write to 0 because we want every position to write to the same pixel. But now we have only one output here. Now we have only one output here. And we said we need one output for minimum and one output for maximum. So we need to set up our MRT. So struct PS output. Float for min pos. So it's SV target, but when you set SV target here, like as with only one output, you don't need to specify the index. But in case you do it per target, you need to say it's SV target 0. So that means it's gonna be the first, like, now you have two texture bound as output. So you're writing to two texture at the same time. So I'll take, so we have our output here, which is minimum position. And we need one output for maximum position. So now we have our output and we're returning one in, we need to change our pixel shader because what we need to do is we need to return PS output. So we need to remove the SV target here. And we need to output something. For the moment, we'll just output 0. Okay, so I'll get you a little time so you can check it around and I'll re-explain. Just let me know when you're pretty much ready. Okay, so now everyone pretty ready or yeah? Okay, if you're not ready, raise a hand. Okay. Sure. Sure. Okay, so now we're gonna continue a bit. So we said now we want the bounding box in world space. And for the moment, we're outputting pixel position, so we need an extra attribute, which is going to be float3 pos world position world. Now runtime complains because I didn't set this. So we need to set the world position. So in that case, we need its output dot. I've put po world. Dot pos world equals like standard multiplication, so mul pos tw dot xyz. So now we have the world position arriving in pixel shader. And what we will do simply is we say our output for the world position it's output dot so we set the minimum position as the world position, which will not work yet, and we actually set the max position as pretty much exactly the same. So now basically for each point our shader will just write world position all the time overwrite. There's no blend or depth mode, so it's just gonna technically the texture will contain the position of the last vertex written, which is not exactly what we want. So we're gonna have to fix that.
But is it for vertex or is it for object?
But well, because it's rendered as point, like you have a point list topology, so that means you have no rasterization, so there's no interpolation when you render as point. The point is just a pixel, and we render to 1x1 texture. So I say the pixel position is actually 0 because it's a 1x1 texture. But then I set the world position in another attribute because I need to access this data in pixel shader.
I just mixed up what
Yeah. So now, yeah, we have the position of the last pixel written, which is, well, at best, let's call it useless. So everyone ready? Yeah? Just see if I switch around. So one easy way to just change it is we're just gonna use, like we have this feature, we have blend modes. So we might just, instead of like, we can just use a simple blend mode to just tell the pixel shader what to do after the pixel gets written. So we're gonna use a new blend mode. Just try to see. So we're gonna use this node which is called blend target, which is a new node. And which is also a render state. So we connect it to bounce renderer. And what you have here is like, so when you have a standard blend render state, either advanced or not advanced, what it does is if you have like two targets, it will use the same blend mode for each target. Blend target allows you to set individual blend pair target. So that means you could say target number 1 I want additive, and target number 2 I want multiply, for example. So now what we can do is we say, well, we need blend enabled. Oops. Everyone done with the code, so it's a bit easier for me to move the patch around. Okay, because it's gonna be a bit, a bit of space, that helps. Okay, so now we have this blend target, so what do we have in there? It's the same pretty much as the blend advanced, so you have which operation you want for alpha, what are the source and destination blend, and the right mask. But now the difference is you can, when you spread it, if you take operation, which is the one which interests us, so we need two of them, and it doesn't spread the render state because it's still one render state but it's per target. So it's still one blend state, but it's a blend state per target. So it's different of multiple blend states. And now we said the first one we want minimum and the second we want maximum.
So does this apply only for this blend target node, or is that something that occurs more often now that it actually looks like it's spreaded, but it's really not?
Sorry?
But for this one, you just said, basically you're inputting a spread of two strings or whatever, but then you said it's not a spread.
Well, it's like you input, it's like the blend, you can have you can bind up to 8 targets at the same time. So you can set 8 render targets at the same time to a renderer. That's the maximum DX allows you. But for each of these targets, you can set up a different blend mode. So you can say, this texture, for this texture, rendering this scene, I want additive. For this part, I want alpha.
I do get it. The only thing I find a little bit confusing is that it sort of looks like a spread, but then it's really not a spread.
No, because it's like, well, I will need to show you code if you want to.
But I'm just asking, does
it's
that
like,
occur like more often, or is that something that in the DirectX11 nodes happen like?
Most of the time you will use a same blend mode per target, but in some case like this one, for example, no. So now we have our blend target minimum and maximum, but we still don't have our nice bounding box displaying, because there's obviously a reason for it. No, it's because actually we have this background color here. So when we need to clear, we need to also clear this texture, because for the moment we clear the texture, but like for the minimum, we always clear the texture to 0. So if we have a negative value on maximum, it will still be 0. So we still need to clear the value. So let's say, actually, let's do it with RGB, cons, color. So it's something you can do with, by the way, which was not possible before. It's from the last build. But when you have MRT renderer, before you could have only one clear color. Now you can have one clear color per target, which makes much more sense. And you can also decide which target you want to clear or not. So the clear is also per target. It's not anymore for all. It's not any or all. It's anything you want now. So now we need to clear this, and it's a floating point texture. So we say the RGB contains the minimum. So what we just simply gonna do, we're gonna do something stupid. We're gonna clear this to 1 million or more. And we're gonna clear that one. Because we need the maximum in the second one, we're just gonna do it -1. And it's still not working. Maybe. Oops. Thank you. Very good point. Yeah, if you try to render to a 1 pixel texture, it's like and it tries to interpolate triangle, most of the time it's gonna fail. So yeah, that's a good point. You need to enable topology. So now you have this alpha box. So now you calculated your whole bounding box, but you have done it completely in GPU. So it can work with any geometry. It can come from stream out. It can come from buffers. So instead of being limited to have to do it in CPU, it can come with any geometry, any type of scene. So normally, if you move things around, it should still work. So I'll just everyone okay on the patch side? Okay, so yeah, to summarize, you just have to clear to a very low value. You don't like texture like normally are 0 to 1, but when you use floating point textures, they can be pretty much any value. So you don't need to do a clear from like black or white. You can put any value you want. So I'll just show the draw bounds, but it's already wrote. I think I forgot to remove the code for it. Oops. But so what it does is really simple. So you have your texture min and your texture max. Then you get your object position, which is a box. And so you can take the min bound, which you just load. You only have 1 pixel, so you load pixel 0. And you only have 1 pixel for the max, so you also load it. Then you can calculate your scaling and your center. And then you can multiply your box size by the scaling, and you move it from the box center. So it's like just it's like if you use the transformation, but because you just have to do a multiply and the add, it's much easier to just do it directly. C'est bon, je l'ai lancé normalement.
Ouais, mais il n'y avait pas la carte dedans.
Ah, forcément.
C'est pas grave.
Okay, so and you just multiply in object space. So now we've done this like very so anyone got question? Need to say something else? No? Yes? Question? No? All fine? Easy? Cool. Okay, so now we're gonna do something a bit different. And actually he's gonna like it as well. Okay, so this one is gonna take a little time to build. Yep. Ah, c'est bon, c'est relancé là. Okay. Okay, so let's do something which I'm sure a few people will find useful as well. So we're gonna have a scene on what we need is we want, well, two things actually. We want to get the closest like vertex that hits the mouse. So like I want to say like no, I'm like my mouse is here. I want to have like a circle here which represents my vertex. So it's like a raycast for geometry. So so the first thing we need to do for the moment, we have this mouse to ray module, which is completely empty. So we're gonna need to create a ray from a mouse position. So how do we do that? So we have the view projection from the camera, which we need to invert. then we have our mouse position. So what we need to do is we need to have our mouse position at the near plane, which means the z is going to be 0. So that's will be our ray origin. That we need to obviously apply transform vector. So this is our ray origin. And now we need to calculate the direction. So what we're gonna do is we need to get the mouse position, but in the far plane. So this is here, but in this case our vector here will be 1 because we're in clip space, which means our depth is normalized between 0 and 1. So that means 0 means near plane, 1 means far plane. Now we can apply transform to this same inverse view projection. And so that's our ray position in the far plane. But now we need to calculate direction. So we subtract far minus near, which gives you a direction. And because we want our direction normalized, because a ray direction, we need a direction normalized, so we need to normalize that vector. Just so yeah, to summarize, you have view projection, inverse, and your mouse position, you get the point at 0, multiply by inverse, which gives you the ray origin. Do the same for the far plane, subtract the far from the near, which gives you a direction that you normalize. So now if you, for people who finished, if you start to move your mouse in the renderer, you could start to see like white triangle, which does intersection. Anyone done with the module? Finished? Okay. Okay, so now what it does is, now you have the ray. What we do is we have this shader, but I will go really quickly on it. But it's basically, well, it's a ray to triangle. It's a ray to triangle raycast. So roughly I send the scene once here for display. And I send the scene once here for ray test. So I do the vertex shader, which is just transform in world space. And then you have all the, well, you have the ray intersections that you can read later. It's not the most important. But what's important is if it's hit, basically every triangle from the scene goes into this geometry shader. But only the triangles which are hit go out of the geometry shader because I don't care about the other ones. So now the stream output here, renderer stream output, contains only the triangle that has passed the ray test. But the problem is you can see this is stream out query, so that tells you how many rays have been, how many triangle intersect your mouse basically. So that for the moment I got 12. So now what we're gonna want to do, two things. We're gonna want to first get the closest one. And second, we just want to show, yeah, we're gonna want to draw a sphere of every triangle hit, but like when we do a stream out query, it's also really bad. Queries are not so great because, well, like, internals are very messy. So a query is something which is great for debugging, but it's really something which should not really be used in production so much, because they can create a lot of errors, infinite loops, slowdowns. So, well, but they're good for verifying the data.
So,
So,
I was going to ask something, mate.
Yeah.
As you know, I did a collision detection DirectX11. We talked about.
yeah, I know.
But I'm really surprised how the one I did only works with one mesh, as in only one type of mesh. So if you put a sphere in it, you could then have 1,000 sphere and it works on all 1,000 sphere. But you can't put a sphere and a box in it.
Ah, but do you use a GSFX or do you use a stream out renderer?
I use GSFX.
Yeah, that's why, because you need to use a stream out renderer.
For the split geometry, the only way is to make a query.
Well, depends what you need to do. Let's say, well, it's quite ugly, but there's an ugly technique which I'm gonna explain now, but you might avoid query at some point. So now we have our triangles here, and we said we want to get the closest point that has hit the ray. So I want to, basically I have this sphere here, very little sphere, and I want it to be only the closest element, but I don't want to get back my elements in CPU with readback. I want to do it all in GPU, of course. So we're gonna use a little, and we could use compute shader, but we technically can't, because we can't even access the stream out counter in compute shader either. So we have to do it in pipeline. We don't have choice. So to do it in pipeline, we have this constant point here. Where I've put something in, out, something. And which is pretty empty. So what we're gonna use it like a trick. So the idea is we need the closest point. So we have a very easy way to get closest element in a pipeline. That's called the depth buffer. So we're gonna use our depth buffer. Like, if you do it in compute, you will need to use interlock min function, and you need to do some float conversion, but it's easy because distance is always positive, so at least it's kinda simple compared to another use case. But because we do it in pipeline, we can use the depth buffer, because the depth buffer is supposed to always keep the minimum value. So what we're getting here is we have our VS inputs, which is we're gonna connect from our renderer. So we have the position of every vertex that got hit by the ray. So we're gonna do more or less the same trick, actually. I don't know why you even need geometry shader for this. Ah, yes, I know why. Yeah, because for the moment here we have a point list, and here we're gonna need a triangle list. So we need to change topology also. So we need to change it back to triangle list because I'm outputting a triangle. So now we have a set of triangles which passed the test, and we're gonna call a draw on here. So now we have a list of triangles. So on our vertex shader, what do we need? We need we already have the position in world space. And we have the camera position. So for our GS, we just need to output. Actually, we can just output the vertex input directly. So we can just delete the GS input and return. Like we can just pass the vertex because we don't need to do any type of processing on it yet. Now, one part which is important. Here we receive a triangle, but what we will want is actually we want to, like with geometry shader, you can transform points to triangle, line to points. You can completely change the geometry. So in this case, because we want the closest point and we have a triangle, we need to output a point stream. So in most cases, you have a point input and you transform to triangle, but in this case, we have a triangle and we output 3 points instead. So it's point stream PS input and GS out. I just make a bit more space for the shader code. And it's VS input here, no? And here it's PS input. Okay, so now, like what we're gonna do pretty much exactly the same as we did in the previous bounding box example. All these points that passed the test, we're just gonna push it all to a 1 pixel texture. So that means, in our case here, the position, SV position is the screen position. So we're just gonna say output oops, it's output dot post equals, so it's a float for 0, 0, 0, 1. And output dot world equals and it's post O. Okay, so now I'll re-summarize a bit. So now we have a bunch of triangles which we already know have intersected. Now what we need is we just need to say, okay, I need a list of points from there. So I just write to a 1 pixel texture, so I can every point will go to the pixel 0. And I need to know still the position of the point because I'm going to need to do some extra operation. Yeah.
When you've got floatable world, using a semantic key.
Yeah, actually, semantic is you can put whatever you want. So as long as it matches from input to output, you put anything you want. So I think I got a bit lazy and just put P. And okay, so everyone okay here yet? Okay, so now just try to give layout space again. now what we need, we say we need the closest point from the camera. So the idea is we have this campus, which is a camera position, and we have divider, which you just put to a reasonable value, which normally should be your far plane. So if you put it to your far plane, you should be pretty safe. So now what we need to do is we need to write, like we want to find this minimum, and to find this minimum we need to write it to the depth buffer. So we're gonna use it in pixel shader. So in pixel shader we're gonna say depth, and it's SV depth. So now that means our pixel shader is, it's not more the rasterizer which outputs the depth. It's now our pixel shader which says I'm taking over. That's I know how to render the depth. So actually we don't really care about color, so we just say color equals 1. We will not even need a render target for that.
What type should depth be?
It's SV depth. Oops, sorry. Yeah, float. Yeah, no, actually we need color, because in our render target, what we need to store, like, we need to store the position of the closest element. So that means in color we can just output our position, but now we need to write a depth in order to that the closest pixel only gets selected. So like, when you don't write to depth, the depth rejection process is done before the pixel shader. So that's what I explained. It's called this early depth rejection. As soon as you write to depth manually, you don't have early depth rejection anymore, because obviously the pixel you don't know the depth before the pixel shader finish. So the depth processing will happen after the pixel shader instead of before the pixel shader. So you reverse the order of the operation in that case. So now we need to have the depth. So we have distance to camera. So basically our distance, so it's from campus and input dot world dot xyz. So now we have the distance to camera, but the distance to camera is not between 0 and 1, and the depth value needs to be 0 to 1 normalized. So what we're gonna do simple is dist to cam divided equal our divider. So we divide the distance to camera by the far plane, which gives us a good chance that it will be between 0 and 1. And we can just say depth equals dist cam dist. So now we're outputting these two elements to this 1-by-1 texture. We output the object position, but we also output the distance to camera. So that means the depth buffer will do the selection for us. So we could have done this with pretty complicated compute stuff, but instead we can just use the depth buffer because it's designed to do this type of operation. So I just leave it for a little bit, and then we're gonna finish to attach the pipeline, and normally we should have our closest element. Yeah. Yeah, maybe that way. Well,
And there is this like out from that. Is there some like performance difference between these? Because it could actually be all like in these parameters.
you mean the float color?
Yeah, no, I mean, yeah, like what's the difference between when it's void PS and it's.
There's no performance difference. It's just how people prefer to write it.
Yeah, okay.
So you could do a PS output struct return with targets. That's the same.
Yeah.
Like the pipeline takes it more or less. If you look at the compiler, it's gonna be more or less equivalent. So it's just like when there is, if you have a lot of attributes, it's generally quite handy to put it in a struct because otherwise you have a huge line. But when you have like, if you just have like, it depends on case really. But there's no performance difference between each.
Even like output is the same, just yeah.
Can I say something like, again, I'm ready, but I should say to everyone, the ticket for tonight's performances you need to get downstairs at the entrance until 4 o'clock. Even the artists who they get that ticket free, but you need to collect it.
There are no tickets anymore, so there are no tickets anymore for tonight.
The artists just getting for the artists. I mean the
10
artists.
minutes before the workshop started, and she said it down. Yes.
Maybe all the artists there's tickets for the artists. But you need to get it. All of them to say that.
Okay, so it's before 4 p.m.
Yeah, so maybe if some people still need to get it, we can maybe make a 5-minute break.
Yeah, we'll do like about in 15 minutes, probably. Okay, cool. All right, so we'll get time to finish this little bit. Well, not all finished yet, but at least one part. So now, so everyone ready? Like, because I'm just gonna switch to the patch again. So now we said we need the closest point, so we just need a renderer. You can use MRT or temp target, it doesn't matter much, so I'll just use MRT. Format needs to say floating point because we don't store really a color, we store a position, so we need the precision. So we can keep this way. We need to go in inspector and set depth buffer. We can keep D32 float, that's fine. So depth buffer mode to standard. One important thing, obviously, is to set the texture size to 1 again. And connect our constant point. Ah yeah, still not connected here. So now we have a texture here which should contain 1 pixel and which should be the closest element that's hit. So normally I've already put it in this shader. And actually, well, it's already implemented for you, so you didn't even have to do anything. So now, like, actually the closest texture just goes in vertex shader and loads the texture 0. And just position the sphere from the closest object position. So now if you look around, like you should have the vertex always the closest one instead.
Which kind of render is this?
It's just MRT, but you can use temp target, that doesn't matter.
Because you have 4 pins because
Which one?
what do I have to change to get the 4 pins in the output?
It's MRT, this one, but you can, you need to go in inspector and set depth buffer mode to standard.
Sorry, Fox, goes back to my comment I made before, but how come you're using this method with an MRT rather than GSFX, buffer out into a compute or a read back?
Well, the problem is you can't access stream out counter for now. At the moment, it's not possible. So the only way to do it is to do a query. But to do a query, I need to wait for the end of the frame to be able to get back the query data, and I have to do an infinite loop to get the data, which is very ugly. So that means it's obviously I can't do it right away because I have to wait the end of the frame before to start the processing of getting the closest element, or accept the fact that I'll have one frame of difference. But now, because here, when you have the stream outs, you have it does it as auto drawing, so it will draw your geometry with the counter. So the pipeline knows the counter, but there's no way for you for the moment to access it properly. So that means you have to use this draw auto function, which is not so great, but so that doing this way that allows you to have only the last element that you can read back quite easily. Yeah.
How is it if you have very high polygon, if you use, for example, tessellation also? Is it dropping performance a lot? Or?
Well, if you do a raycast on all, yes, that's gonna hurt a bit, of course. But this one doesn't do the tessellation, so it depends. If you want to start to do a vertex snap, I will do it on non-tessellated geometry because it's normally you could even send simplified models for it. It depends what you need on your use case, obviously. Yeah, it really depends on your use case, but this one is quite handy to select quickly a point on a model, for example. And especially if you have a bit of low poly, if I remove the spheres, and I'll take a little less, yeah, otherwise it's quite hard to select the right point. So it's much easier to select if you have very high poly geometry, you will be the same as if you look up on a texture. But when you have low poly, you really want to get the corner, it's much easier to snap this way. So yeah, everyone ready? Got it? Yeah. Question?
On the stream out render, it's got the vertex size and element count. Is that relevant for this patch?
Well, I can explain it quickly. It's basically arbitrary. Well, no, not completely. The vertex size is 16 because I output a float 4. So I output 4 floats, so each float is 4 bytes, so I need 16 bytes vertex size.
Okay.
So it's the size of your vertex structure.
Yeah.
So if you put a position on the color, that would be 32. And element count is actually maximum size of the buffer, because there's nothing as dynamic sized buffer. Actually, even in programming, it's you always have a. So I just generally select size which will be over what I need in general. So in that case, 512 is generally will do the job, but so it should always be your the element count is the maximum size of your buffer, so it could be 1 million, but then it's only the counter which decides. So when I call the draw here, it's gonna call a draw with the counter. So even if I have a buffer of 1 million elements, it will still draw. In that case, 8 elements, because it knows only the 8 first are relevant. So it's not.
Vertex size is like the stride.
Yeah, it's exactly the same. So yeah, it just allows to avoid query around, which is quite handy. And well, yeah.
It's really useful for having a good camera shot, right? Having a good user operatable camera.
Yes.
Something which we haven't never really added before, right?
Huh?
Something we haven't really added before.
No, that's something I added in your mapping tool at some point.
Cool. So in frameworks, there's a thing called wrap down.
Yeah.
It takes a 3D position of the cursor, and it works like SketchUp. If you rotate around a position.
Ah, yeah, okay.
Against that position,
Yeah.
things like that. Now, obviously, to make that V4, the
Yeah, yeah.
But is that other method much slower than this method? Or
It's as usual. It depends. So, well, if you raycast, what you can do, you can always optimize, because you can say you can do you can first select. You can do a raycast on the whole sphere first, and if the sphere is not passing the ray test, you can discard the sphere.
Sure.
So you have a lot of room for optimization as well.
But for instance, with the depth buffer, you've already got it for free because you're already making it, right? So
Well, yes, for free, yes and no, because obviously you have to write to it, so that's not free.
no, you only have to read from it, it's already there, right?
No, well, obviously writing to it is also costing you something. Even if it's under the hood, it still costs something to write to depth buffer. To write and read.
Yeah.
So it's not, well, it's free, but it's not free.
Yeah, the writing is free and the reading is not free.
Yeah, yeah.
So you have to,
Yeah, but you have it out of the box, so you don't have to do another target compared to what you had to do before, yes. Okay, so I think, well, if you wanted the little break, because the second part will take more than 7 minutes. So if you want to do this little break to check, we can do that now. Okay, so now we're gonna add something. Now what we want to do is, like, you have this show all toggle. So what we want to say is we want to show every vertex that's been hit by the ray. So, like, the problem is, well, we want to show it as a sphere, so we're gonna need to instance that sphere. So if you do it in compute shader, you have append or counter buffer, so you can do indirect draw. But as I explained just before, we don't have access to the counter here. So we need to find a solution to get this counter without leaving the graphics card. So we have a very ugly solution, which, well, in that case, because like our array hit is not very big, it's like 30 elements, so in that case, in that use case, it's okay. If your counter was 1 million, that's not usable, but in a simple case with even 30 elements, it's not a big deal. So now the idea is we switch to show all, so for now we have one sphere because it's not instance and there's no data for it. And we want to say, now I want to display every single sphere that hits, like every point at the edge of each triangle should be a sphere. So if we don't want to leave the graphics card, we'll still have to find a way to do it using indirect. But we don't have access to counter, so we're gonna do something stupid. So we have this shader here, which is called build counter. And for the moment, there's nothing in there. So we're gonna take a texture size here, and we're gonna render again in a 1x1 texture. And we take our geometry and we send it to the build counter here. So don't forget for now we're still drawing points here. So we need to draw points in that case. So we're gonna draw our geometry to this 1x1 texture, and we need to set the format to R32 float. So we need only one channel basically. So now, like as usual, to draw into a one, I just try to organize workspace a little bit so people can see a bit of both. Let's move the renderer out for now. So what we just want to say, we just want to say, okay, we have a certain amount of point here, which is like the same number as output of stream out, but we want to store it somewhere in the graphics card without leaving the graphics card. So what we're gonna do is do it in a very stupid way. So we say we have a 1x1 texture. So our screen position is gonna be again equal to 0, 0, 0, 0, 1. So for every point which will go through here will just be written in the single texture. So it will all be written. So what we're gonna say, we're just gonna say return 1. Because for each pixel we want to say add 1, and to add 1 to the texture we have something very simple on the pipeline for us, which is called blend add. So now, like to summarize again, so we have this renderer which contains an unknown amount of geometry which we don't know about. We send it to this build counter shader. So every point will be drawn once from the vertex and will be drawn at location 0 on the texture. And it will return 1, but because it's additive blend, so every point will add 1 to the texture value. So that means now in our texture, so now in our texture we have the same value as in the stream out output. Now we're gonna write a small compute shader which is going to be extremely hardcore. That's the only compute shader for the workshop. So now the problem is we need to feed this counter. Who knows about indirect draw? Okay. Okay, I'll try to explain it. Well, it's normally more for compute workshop, but I'll explain it quickly. So when you draw geometry, you have arguments to the draw call. So for example, if you draw a list of points, you have like 3 arguments, which is how many vertices you draw, and I forgot the 2 other ones because I never use them and they are 0 all the time. Yeah, because it's a draw instance, so it's gonna be much easier to explain this way. Yeah, you're gonna have to see a little bit of code, but that's gonna be much easier to explain. No, that's this one, resource. Okay, and like if I take, for example, vertex instance, which is the one we need, that's the one. So like basically when I ask to do a draw call for the pipeline, I have to provide this argument. So like this call says, this is how many vertices I want to draw. This is how many instances I want to draw, and that's for start location. But in that use case, you normally keep it to 0, so it's not a problem. So, but what you can see is these arguments are provided by you on the CPU. So you have to be on the CPU to tell which number of elements you want to draw. When you do indirect draw, the difference is these elements are contained in a GPU buffer. So instead of sending a manual value, you can send a buffer to your graphics card which contains this draw information instead. That's how indirect works. So that means we need to prepare one buffer, which first element will be vertex count, second element instance counts, third element 0, and fourth element 0. That we need to write to create this little buffer. So now in our texture we have this pixel, so now we need to write it into a single buffer. So we're gonna need a renderer buffer. which has element count of 1, because we have only 1 pixel, so we need 1 element. And we need a stride of 4, because it's going to be 1 number float, or 1 integer. And it's called, you have this in your list, which is called copy texture counter, which is our hardcore compute shader. So it has 1 texture input already. We have only 1 element, so we need a dispatcher which we keep as 1, 1, 1. So we do a dispatch, we send 1 element to the pipeline and connect it here. And actually it's already implemented for you. So I'll just explain the extreme code. It takes the 0 pixel and write it in the 0 buffer. That's it. So it's just like to convert a 1 by 1 pixel to a 1 buffer. That's it. Because it's after to do indirect, we can't really easily copy from texture, so it's easier to copy from buffer. So we need to do this little 1 by 1 pixel to this 1 element buffer. So now our counter was here, it's been in this texture. Now it's been copied into a structured buffer, which has only 1 element. And now we need to say this buffer is actually our instance count. So that's how many spheres we need to draw now. So to do that, we need to use also a new node. Which is called, you have index indirect drawer and index indirect buffer now. So you need to take index indirect buffer. So now we go in the inspector. And you can see you can now override properties of the buffer. So what we want to keep the index count. We want to keep the index count because the index count is per sphere. But what we want is we want to override the number of spheres we want to draw. So we need to show those 2 pins, which is the instance argument, and that's the resource offset, which in our case will be 0. So that's not a problem here. So now you've done with this, you connect this buffer to the index buffer, you connect the sphere as input, and you connect the sphere as output. So now you have this counter which did all this little way, and now this counter finally made its way as an instant count for our sphere. Which was a bit tedious, but well, it's still nicer than readback. So so now we have this bunch of instance sphere, but we still see nothing, because we need to obviously find the position of the sphere. So here you have this buffer out pin. So when you write to stream out, you have 2 different views of it. So you have the geometry view, so it's like just a vertex buffer. But you also have the buffer out, which is a raw buffer. So that means you can use it as a, like it's called byte address buffer. So you can access this as byte address, which you can connect to your shader here. So buffer out needs to go into raw position buffer here. And obviously we're gonna have to go implement something in the shader, which is not gonna be rocket science either. So everyone ready? Yeah. Okay. Well, basically, if you're not ready, say no. That's much easier. Okay, so now, like we have our row position buffer, and which is byte address. So that means it's like just bunch of memory, but you, like when you use a structured buffer, you already know how to interpret the data, because you say, okay, this element is a float for, this element is a int, so this element is a structure, so you already interpret the data. A byte address, you have to interpret it yourself. So actually, more or less everything in DX11 is just raw buffer. It's just when you write a structured buffer, it's gonna do exactly what we do, but it's gonna do it for you instead. But in this case, we can't have stream out unstructured buffer at the same time, which means we have to do it manually. It's just a pipeline limitation. There's no choice about it. So, like raw buffer only, let me remove that one. Raw buffer only accepts ints, and what we said is like it's really like in memory, so you have to think it in byte space. So it's like everything is a byte. So that means first, if we need to load, we know we have a float for. So a float for is 16 bytes. So we're gonna add the first part, which is int stride equals 16. And now we need to load this float for. So to do it, we have this instance ID here. So we need to say float for position, position equals, no, we'll do it first. So we need uint for row position equals, so it's row buffer and it's load 4 because we want to load 4 elements. And so that's instance ID, but we need to, because we are not in array space, we are in byte, we need to multiply by the stride. So now we have our position, but our position is still this uint uncoded data. So we need to interpret it ourselves, but it's not so bad. So it's float for, and what you call is as float row position dot x as float row position dot y as float row position dot z and as float row position dot w. So now we have the real position in our instance location, and we have already our screen position here, and we have like that's the position of the vertex. So we do exactly the same as if we were using structured buffer now. So it's just post.xyz plus equal, I just change the name for that, instance position dot xyz. Actually, I said by 16, but by stride. Normally I will do by stride, but it's exactly the same, it's just so I can change it only in one place. Okay, yeah. Still not displaying anything. Sometimes it. Okay, so what we can also do if we want is to do read back buffer buffer int. Ah, it's not copying here. Okay, that's probably, so yeah, it's still drawing 0, so that's why it's not working. So give me a second. Okay, it's not doing anything here. Why? Okay, yeah, you can use query to verify data. That's always useful. Because for now I got a little issue. So that's, as I said, it's very good for debugging. So what we can do is also, actually, like you should have exactly the same result on the occlusion, but that's why it's not working here. Because occlusion query should be the same as a stream out, because obviously, because we've write 32 pixels, but here none has been written. And it's not scrolling. That's a bit strange. Okay.
The geometry. No.
No. That's just not going to pixel. I should be on point list still here. Ah, there we go. Sorry, I forgot. Yeah, because the stream out. Yeah, I forgot. But stream out renderer stream out defaults to triangle list. But because obviously, if we send triangles to like if we send a zero size triangle, like it will not go in the pixel shader, it's gonna be discarded. So we need to make sure like the topology is point list. Then it can go to the pixel shader. So if I reduce my sphere, okay, and now it's working.
Sorry, mate, could you briefly explain a little bit the idea between the renderer streamer? Just because generally, when it's baffled me before, and I just end up using geometry shaders to
Well,
stream out rather than.
the idea of renderer stream out is you can have one, with GSFX you have this one input, one output.
Yeah.
With stream out, the idea is you can send multiple layers to the same buffer. So that's not really easy to do in GSFX because you don't have this layer input, it's geometry in, geometry out. So it's good for processing like individual geometry. But if you want to do a whole scene, you need a render to a buffer, you need a renderer stream out, and then you can use layers. But the code in the FX file is almost the same as in a GSFX. It's just you can use, like I can add a second geometry shader that outputs exactly to the same buffer. So yeah, now you can see every object which has been hit and you didn't leave your graphics card.
That was the problem is the readback, that you first have to draw it all and then you cut the result of the readback.
Which one?
Sorry, why didn't we use the readback?
Well, the problem is if you do a readback, you can use a readback for the closest element at the end. Because if you want to get the closest point, what you will need to do is get all the stream out data. You will need to wait, you still don't have access to that counter. So that means you still have to wait 1 for the query, 2 for the readback. Then you need to get all the points that passed the test. Then from this, you also need to sort them in CPU. Whereas if you need only the minimum element, so it's like you can all process this in graphics card, and if you want, you can just do a readback right at the end only for the closest element. So you do a readback on 16 bytes instead of much more data. So the idea is if you want to use readback, it's good to try to reduce as maximum the amount of data you want to get back, especially for this type of processing. Sometimes you want to get back the whole buffer for saving to a file, but in that case, just like, yeah, in that case you just need the closest element. So
can you show us once more the solid color route position?
yeah, sure. Okay, anyone got more question or need a bit more time? Otherwise I'll go to the next one. So if you need more time, let me know, and if you have any question, please ask.
Just one more thing, can you highlight the instance position?
Yeah. Yeah, I got this custom highlighter, but I forgot to put it in the material pack. So I'll give it to you after the workshop. So it's just like there's all the highlighting for DX11 in the code editor. And finally dark theme also. So yeah, okay, so now we've done something a bit more. Okay, now we're gonna start to go into anti-alias. So we we're gonna open this MSAA coverage. I'll just bypass the sample index one because well, we don't have that much time. But you can. I'll give the finished patch, and it's quite easy to grasp anyway. So now we're gonna go to anti-alias. So when we render primitive here, we have this AA samples per pixel, and well, it's not so nice to set it to 1. We generally want to have a bit better value, let's say 4, because obviously people don't like aliasing in general. So the first thing we're gonna have to see a bit how it works for a primitive. So basically you have this thing called coverage. So basically when you put this pin with more than 1, you don't have to think in pixels anymore. You have to think in samples. So a sample is like a sample is like a sub-pixel. So if you're like on 4 samples per pixel, it means for each pixel you have 4 samples, and each with some sub-pixel offset. So you have different offsets on your pixels for your samples. And when you finish to render to this texture, then there's a process which is called resolving, which is gonna take this sample and average them to give you this nice anti-alias that you can see when the standard AA usage. So how does it do it? Basically you have this thing which is called coverage. So what we're gonna see is we're gonna look how it's implemented inside. So we need first, I'll just move the renderer a little bit. So we have this input, and what we want to do simply is we want to output the coverage. So basically that means for each pixel we want to know how many times, if it's a full pixel or if it's an edge pixel. But it's on the geometric way, so it's not like it's an edge pixel on triangle geometry. It will make sense once we have it. So to output coverage, we already have here, we need to add this primitive uint coverage, and it's SV coverage, very original. So coverage is pretty much like just a bit field, basically. So it's gonna say this sample is part of this geometry passed for this sample, but not for this sample. So if you have like 1 everywhere, that means you have a full pixel. So we just say return input.coverage, sorry. Okay, so now we're gonna be able to, now we need to visualize this coverage. So we connect this buffer, and why is it not here? So yeah, we need to add our texture here. So texture to the coverage, and you need to strongly type it because it's a uint texture. Coverage texture, and now we need to get the coverage which I've set to 1 by default. So now it's our coverage texture dot load, because we are not allowed samplers in that type of texture, so we have to use load anyway, and it's faster. So int3 p.xy 0. So now we can finally connect our buffer here. it should be R32 uint as well. And
show the other shader code?
yeah, sure. So the only two things you have to add is uint coverage here as pixel input. And you have to say in the PS coverage only, you have to return the coverage basically. So you just output what the pipeline provides you. And yeah, technique is already correct. So it's fine, yeah. So now we have this coverage texture and we have this function called isEdge. So we're gonna obviously have to write that function. So if I say return true, no, it's just gonna say if it's an edge, return white. If it's not an edge, return black. So one thing is coverage depends on your MSAA levels. So that means here, basically we have 4. So it's, and that's 3. Okay, let's see. Okay, that's normally fine. And that should also be fine. Or did I mix up something? No. Okay, this one decided to be not happy right now. Right. It's quite hard to do preview. Hmm? Yeah, I tried to just return it, but it's still the same. No, it still doesn't like. It's quite strange. I need any. Ah, okay. Okay, that's one not working for now. Okay, I'll have to get back the example because I got something wrong in there.
Maybe can you explain the theory, like what it's supposed to do?
Yeah, actually I probably have the working code somewhere, so that's gonna be easier to check it again.
So when it's working, is this making like something that replaces the anti-aliasing option on the render itself?
Yes, kinda. Okay, I'll explain you in a second.
Show us later, yeah.
And it's in. Yeah, but it might. Is it? Okay, well. Okay, I'll double check if that's fine, otherwise it's me who is somehow stupid. Yes, that's me who is a bit stupid actually. Okay. Okay, so let's not change the, go back to the old code, R32 uint and uint. Okay, it still doesn't work. Okay, that's different, but still not.
Also, here maybe we can change before PS to unit.
No, that one is the color after. Isn't it with? Yeah, but it's. Yeah, that's because it needs to be. Yeah, coverage is not per pixel. Oops. So that's per sample. So that means we need to do a texture to the MS instead. And its function is load. And it. So it's not int. It's got a bit all mixed up, so let's do it properly.
What's the MS stand for?
It means multi-sampled. So I'll just explain that in a sec. And we need this one. That's better. Okay. Actually, I wanted to add too much little tricks around, so I just lost myself a bit. Okay, that makes more sense. Okay, so we got, so coverage viewer didn't change. No, yeah. So what we changed here is like, so we need to put texture to the MS because the coverage is on the, like when you use the texture 2D on the buffer out, the texture is already resolved, so the coverage doesn't exist anymore. So that's why it was returning me no data. So you need to use texture to the MS, which means this texture still has information about samples. So now, the one difference is you need, in the renderer, the temp target, also, you have this, like you have this pin called AA texture out. So you need to connect the AA texture out to the, and not the buffer out. You need to connect this AA texture out to the, because like the buffer is already resolved, so it's not a multi-sample texture anymore. It's just a simple texture. So you need to get the real multi-sampled one.
Is that really like 4 HD textures now?
Hmm?
Is that really like
It's yeah, it's for HD texture at the moment. Normally that's And no, it's not 3, it's 7. Oops. Okay. Un, deux, trois, quatre. Ah, ok, c'est 15 dans ce cas. Ouais.
Julie, how can I do it? Just come online and start in that moment.
Okay, so now, okay, now I'll just quickly re-explain. So the idea is now we have all these individual samples, and we want to get edge pixel, which is a very important thing for shading, basically. So what we do is now we can't use sample on a multi-sample texture. That's like, because it has no, it also contains too much data, and we have no MIP maps, so we have to say load, and we only need to get the center pixel. So that means it's the center, like that's the center sample. You need to change, if you have this error, you need to change VS5 and PS5, by the way. If you have an error compile, because it's not, you can't do it in, and that should be okay now. Nice. Yeah, because when you change to MS, it disconnected it. Okay, so I'll just quickly re-explain. I just explain the edge check. So basically, you have this coverage, which I said is a bit field. So that means we have 4 samples per pixel, so we have a bit field of 16. If we add 8, it will be 256. So it's like every time you add a sample, it's like a power of 2. So it's like, because we have 4, it's 2 power 4 minus 1. So if your sample coverage is 2 power of the, because it's a bit field, so it's 2 power of the sample count, and minus 1 because obviously in computer we always index by 0, then that means you have an edge pixel. So the most common usage for it is we use that for stencil. So we always reserve a bit of stencil for, so we do this edge detection because when we do complex shading, we need to have, like sometimes we need to use light per, in some light per pixel is not good enough. So we need to use light per sample, but obviously if we do light per sample, that means for each light you process full HD by 8, which is kinda, well, let's call it hertz per light. So now so if we want to do per sample, what we do is we do this stencil pass. Then every edge pixel will go into the per sample shading, and we run 2 passes per light for the same light. So we run 1 pass with the stencil wrong, so any non-edge picture will be shaded per pixel, and any edge position will be shaded per sample. So that's one of the common usage for it. But we don't really use coverage because it's a bit wasteful, but you have other formula for it. But that's quite a very easy way to debug also. So now we've seen we can actually, well, here we just outputted like raw coverage, but actually we can really output the real coverage. So that's what's gonna go in the next sample. So we're gonna finally go in the transparency. Okay, so we have quite a few ones around. So we have this alpha test first renderer. So we just have a little plant. And for the moment, it does nothing. So we're gonna implement alpha test, which is very, so we have a texture which is 4 samples per pixel. And we're gonna do this alpha clip, so standard alpha test, because obviously if you look, if I take a camera, you don't need to do that. It's just to explain. Okay, and if I do. I already have depth buffer, that's perfect. So if I have this alpha texture, and now I say I want 2. And I need to do it on the Z. Yeah, for the moment you can see this texture is masking, this plant is masking the other plant. So we obviously don't want this. We want to be able to see a bit of both. So the standard way you did in DX9 was called alpha test. So it was a render state at the time. Now you have to do it in shader. So you have this alpha reference value, which is the one you use to put in alpha test. And you have this simple pixel shader which just samples the texture. So it's just a constant for the moment. So now we need to implement alpha test. So you have 2 ways to do it. So you can say if color dot alpha ref discard So now we say anything under this alpha value, we just discard the pixel, which also discards the depth buffer. So that means now we see our 2 elements together. But you're gonna see it's looking really ugly. Well, it's not really easy to see it on the projector, but if you look on your screen, you can probably see quite a lot of aliasing. It's not as obvious on the projector. So now you can change your alpha reference. So it's like very aliased, because when you do clip or discard, you discard the whole pixel. You don't discard individual samples. So that means you, even if you have the 64 samples per pixel, which is not yet possible, if you use clip, you will go back to the 0 or 1. So it's back to the all or nothing. So you have no anti-alias option using discard. If you actually, if you want, you have another option from discard, which is the one I generally use more. So you just can comment that out and you do clip color minus reference. So basically clip works as subtract this value, take this value, and if this value is less than 0, discard. But it's it's pretended it's a bit faster, but I don't trust that things too much anymore. So it's up to you to try. Sometimes clip is better performance-wise, sometimes discard. So, but well, that still doesn't solve the problem. That we know back to, we have this anti-aliased texture, but we have aliasing again. So anyone done with alpha test? Yeah. Okay, so now we need to find a solution to have this with anti-alias. So you have this option called alpha 2 coverage, which is just in this case a render state. So you need to use rasterizer advanced. Is it no? Is it blend or rasterizer actually? No, it's actually it's blend.
Blend advanced.
Yeah, it's blend advanced. Yes, right. Yeah, that's the one. So you just take blend and you just put alpha 2 coverage on. That's it. You don't need to do anything else. So that's gonna be your second texture, which looks slightly better, but really blurry. Like, yeah, you need to zoom quite a bit if you want to see. So yeah, alpha 2 coverage, you can see it's quite blurry. So it's more like blurring the edges. So now what we're gonna do, so we can have the coverage as input, but we can also actually output our own coverage. So we can decide ourselves how much, we can decide the coverage ourselves. So now we're gonna open the alpha coverage shader. And I just put that one here again. And so alpha coverage. I don't know if that line's here on yours. So if it's not, put it. So you need to put the MSAA sample, which is equivalent to the one in your renderer, otherwise it's not gonna work. And you can see in PS output, we have this coverage output. Here. For now, you don't need to write anything. So we still have this alpha reference, which is the same as for the per pixel one. And we have this include, which is MSAA offsets. So that's the pixel offsets that I'll explain in a minute. So now what we're gonna do in this example, now we're gonna say for the moment our coverage is 0. So that means if our coverage is 0, that means actually no pixel gets written. So we have, that's the screen space derivative for texture coordinates. And now what we're gonna do is we're gonna do subsample looking. So okay, so we need first to loop. So we're gonna loop through, we're gonna do this, instead of like for each pixel, we're gonna do sub-pixel lookup ourselves basically. So we're gonna do a sub-pixel lookup and you're gonna tell, okay, this passed the test or not. So int, we need an index which is equal to 1 for the moment. And int equals 0. Ah, no, we don't need that, I think. Okay, so now we need to do the alpha test again, but we say we can't clip, so in that case we need to so we need to sample our texture again, but we need to use this MSAA offset, so it's like this variable here. That one too much. So it's texture. Not sample. Okay, I'll just explain it a bit. Okay, the idea is, so for each sample we're gonna get this offset, and we're gonna grab one sample which is a sub-pixel sample, and we need to do the alpha test on this sample. So in that case, it's if it's greater than alpha ref, then we have our color, so color plus equal sample. So we need to add our color. So if we pass the alpha test, we need to add to the color, but we're adding a sample, we are not adding a pixel anymore. So it's like when you do a blur in some way. So you do a small blur, but it's a small blur per sub-pixel. And normally output dot. So it's color dot RGB divided equal dot color dot. And output dot color equals color. Yeah, I'm just gonna explain it in a second. Sorry for closing the thing. Okay, so now, like, what we also need to say, because now I'm outputting a coverage of 0, so that means technically nothing gets written. So we also need to say if we pass the test, we need to also say this sample passed the coverage. So for the moment our index is 1, so you do output dot coverage. Oh, or equal edx, and at the end of the loop edx multiplied by 2. So it's almost there, but the offsets are not right yet. Now it's outputting. Just clean up what's not needed. Forgot what the DX. Okay, so yeah, that's fine. Okay, so I'll just explain the code properly. It's only on this pixel. So what we do is we have this final color, which I actually don't use. We have a color which we start with a black color and a coverage of 0. So coverage of 0 means no pixel, no sample really needs to get written. So if you output a coverage of 0, basically the pixel shader will not write the pixel. So now you have this, like that's the derivative, so that allows you to get like a small XY offset. So you start with this index. You can do bit shift, or multiply, that's the same. So you can choose, because you have to write a bit mask. So that means for the first sample, for each sample, you get the offset for the sample. You have to multiply by the derivative. And actually it should be float to dx.x dy.x. Yeah, it should be this one. So you multiply the offset by the derivative. It's almost like dividing by the, to simplify, it's like dividing by the resolution, more or less. So now you have this sub-pixel location that you sample like if you were sampling your own texture. Then you process your alpha tests. So if the sample passes the alpha test, then you need to say this sample needs to get written. So you have to, you update the mask by setting the bit to 1. So that, for example, if you have like, it's exactly the same as before with the toggles. So you just write these 4 bits to say, okay, but on this case, it's only 4. So what you do is you add the color because what you want to do is an average at the end. So you need to average every sample, otherwise you don't have any anti-alias. And so you get the sample. If it passes the test, you output your coverage by setting the bit that I multiply by 2. You can do bit shift if you prefer, but I find multiply by 2 is easier for some to understand. And you add the sample. So the advantage of using RGB divided by AAA, it gives you a weighted average, so it's better quality average. If you add 1 and say, if you have only 3 samples that pass the test and you divide by 3, then you have a non-weighted average. So that means here, because you also use so the higher the alpha value, the more importance your subpixel has. So that gives you a weighted average. So that's why I divide by the AAA. and then you output color and you output your coverage. And from this information, your pixel shader will manage it itself, basically.
Okay, what does this line say exactly? Output.coverage is not.
It's or equal, so it's binary operation. So that means it's like, because it's a bit field, so that means like the first sample is value 1, the second sample is value 2, the third sample is value 4, the fourth sample is value 8. Okay. So it's like a flags in C# in some way, or in any programming language. Flags are always power of 2, and when you do or equal, you say enable this flag, basically. Hmm?
It's really nice that outcome from that.
Yeah, it's like, well, the problem with clip is you always have this aliasing, and then you have to use FXAA for sorting it out, which is, well, for some cases okay, but for many cases not ideal, especially when you have a lot of very thin objects, like FXAA is really not that great. If you have just line, it's okay, but if you have thin object. So yeah, well, you can see it's quite really easy to see the difference of quality in the output.
Where would you use it? Like, is there of course like leaves or?
Yeah, well, leaves, trees, anything like billboards. Like leaves, trees is the most.
Or like just like particles?
You can use it for particles, but it's a bit expensive, so it will depend. Like for just simple circle, if your particle is just a simple circle, FXAA does a good job at fixing it, and doing it per here is a bit expensive still. Yeah, you have to process for each pixel, and you give extra work after the pixel shader as well. Because when the pixel shader is finished, it has to process data differently depending on the coverage you provide to it. So it's obviously more expensive, but, well, higher quality generally means more expensive. There's no... Okay, that's weird.
Yeah, I have also some glowing edges.
I also have glowing edges.
And if you tune up FRF, of course you take it down, so then it gets edgy again.
Yeah, you have to. Yeah, alpha ref needs to be tuned quite properly as well for that, though. Yeah, you need to have you need to find a good value for ref, but it's no maybe. Yeah. Let me check. I didn't write something wrong. Yeah, okay, that's my offset, sorry. I messed up my offset calculation. Yeah. That's probably why it's not working for you. Yeah, sorry, I messed up my bad, I messed up the offset one. So that's why you get the glowing edges. Because you're not sampling in the right place. Now it should be no more glowing edges and nice. Yeah, you'll have glowing edges with really low alpha value, but that's quite normal, I think. So you need to find a bit of sensible value for it.
But then I don't see any anti-aliasing.
I don't know, I've put alpha ref to 0.5 here.
Doesn't really go to about 47.
Oh, 0. Here it's still. Do you have the one I gave you actually? Can you put it? Yeah. Just double check it. Okay, we'll recheck it in the next one anyway. So we're gonna reuse it in the next one, so we might check that at the same time.
You put it on here?
Yeah, can you put it here? Just double check I didn't do something. Oh yeah, because actually you have all the. Where's my folder?
No. Check on. My folder.
The one I gave you.
Yeah.
Maybe here.
But
Yeah.
I think it's all.
Yeah, but grab here. Alpha to cover alpha.
This one.
Yeah. No. Alpha coverage. Done. Done. Ah, fuck, it's already. Ah, yeah, okay.
Obviously, it's the weighted.
Yeah, it's the weighted one.
If I take it away and just divide it by a counter that I added to the if, that's fine.
Okay, you can do the weighting here too, actually. That one. Yeah, it depends how you have the weight, but I think you don't have specific case for it. So if you remove the weight and put fixed value, it.
Just a counter that's counting in the if is true, and then I divide by the counter.
Okay, let's see if it's not weighted. Okay, yeah. So I guess it depends on smaller or larger value. So sometimes it's better, sometimes it's not. So, okay. So yeah, you can use a static divider if you prefer. Okay, so we're gonna go to the last patch and we're gonna go back to that anyway. So we're gonna do a bit of things with all this stuff we've done today. So we're gonna open MSAA transparency large. Okay. So we have a preview, which is just a stupid field here. So what we're gonna first want to do is we're gonna displace a bit this field. So we have already a small Perlin texture organized here. And we have this constant wrap here, which is just displaying the field. So we need to do a bit of displacement on this. So, well, it's just a standard displacement. So that's our texture displacement. And we need to add a transform as well. But we don't need texture transform. It's going to be quite important that we need to use world positions for that. So it's just a standard. So transform displacement. So up to here, nothing too fancy. Now we obviously connect our Perlin to our texture displacement. And we connect our transform here to the transform displacement. So now we still have nothing which is logical, because we have to implement the displacement, which is not going to be too bad.
So where do I get the texture input in the constant wrap?
It's from the Perlin.
Yeah, but there's input pin.
And the other one is transform.
Where's the code line to get this?
It's tdisp here.
Yeah, I added this, but I didn't get this.
Okay, so now what we need to do is we need to displace this slot. So we're gonna say float to disp equals, so it's text disp dot, and in that case it's sample level, because we can't we don't know the MIP index in vertex shader, so we need to use sample level. And we have our sampler here.
May I ask the question again? Because
yep.
the Vulliet output with the first pin is a texture and not a transform.
Sorry?
Yeah. The first output here is a texture and
yep.
not a transform.
No, the transform is this one.
But this, yeah, okay. And here, I got sample state and the
So first we need to compute our 2D positions. So it's 2 xy equals input. So in that case it's like a grid which is rotated. So the grid is in xy, it's in xy plane, so that means we can just use pos o.xy. Now we need to say we need to convert it for UV, because we want to sample with world coordinate. So we need to multiply pos xy, it's float for pos xy 0.0 1.0, and we multiply that by our displacement texture and .xy.